Alright, so section 8.1, we're going to be dealing with systems of equations. Now this chapter 8 all deals with systems of equations and some of the related mathematics involving matrices. But for right now we're going to start with systems, and this first section really is a big review of some things you've probably seen before, but we're going to go over it. So there's a lot of content here in this one section, a lot of content in one small section, and so it may look like a lot, but really it's hopefully things you've seen before, shouldn't be all new to you, but maybe you need to knock the rust off and see it at another time. So starting off, what is a system of equations? So by definition, a system of equations basically is a set of two or more equations solved simultaneously. Okay, a set of two or more equations solved simultaneously or solved together. Okay, and the solution, when you solve it, the final answer is going to be some sort of point. And we're going to call it the point of intersection of the graphs or of the equations. Okay, so the solution is the set of all intersections of the equations. Okay, all of the intersection points. Now let's just take an example. We'll start with those two definitions, kind of look at an example here. And so the example I'm going to choose is going to be negative x plus y is equal to 1, and 2x plus 2y is equal to 6. So here I have two equations. So now it becomes a system of equations. I've got two that I'm solving simultaneously. The two equations each have two variables, so these are going to end up being lines on a graph. And in fact, if I were to plot the graphs of them, I might be able to identify where this intersection point is. So let's go ahead and do that. In order to graph these, I'm going to use the x and y intercepts of each one. So maybe I'll take these off to the side here. So this first one, I'll do that in the green pen. So I'm going to take the x-intercept for that first one. Remember, you set the y value equal to 0. Solve for x, you get negative x equals 1. So x must be negative 1. Then the y-intercept, that's where you set x equal to 0, and you'll end up with just y equals 1. That's it, right? When the x goes into 0, this term drops out and you get y equals 1. Okay, so the 2 points on the graph there are going to be negative 1 comma 0 and 0 comma 1. Alright, so now for the other equation, so that was the green one. Let's do the other one in purple. Just change the color up a little bit. Alright, let's slide this up. And so let's do the x-intercept. Again, the y value starts out as 0. If the y value is 0, I'm going to be left with 2x equals 6. Divide by the 2. We get x equals 3, so that's an x-intercept of 3 comma 0. And then the y-intercept x becomes 0, you get 2y equals 6, divide by the 2, y equals 3, so 0, 3 is the y-intercept. Now if I were to plot these two graphs, make a quick sketch. This first graph is, let's see, -1 in the x direction and 1 in the y direction, and so its graph is going to go up to the right. Not too bad. The second graph is going to be 3 in the x and 3 in the y. So 1, 2, 3, and we already have 1, then 2, then 3, and that one is going to go down and to the right then. It's going to connect 3 to 3. Okay, and so when we draw those two graphs, every point on each graph is a solution to that individual equation, right? So all the points on the green line are solutions to the green, or this first equation. The points on the purple line are solutions to the second equation. But there's only one point that would be a solution then to both equations, and that is the point of intersection. Okay? And if we just kind of eyeball it from the graph, that point of intersection appears to be at the point 1, 2. And we'll check to make sure that that works. Remember, it has to solve both of the original two equations. So if I plug 1 for x and 2 for y, in the first equation, we'll do that in green, I would get -1 plus 2 equals 1. Of course, we're checking to see if that works. Well, of course, -1 plus 2 does equal 1. Okay, so that one checks out. And if I put that same ordered pair in the second equation, I have 2 times 1 plus 2 times 2 equals 6. Alright, we can, let's see, simplify the left side. Again, I should put a question mark there. Simplify the left side, that's 2 plus 4. 2 plus 4 is 6, and 6 is equal to 6, so that one checks out. Okay, so as long as those equations are solved, and they end up with true statements at the end, then that point did work out. Now there are some weird cases of systems. This was a nice one where the two graphs intersected once, but there are a variety of other scenarios. There's a scenario where you have no intersection. Okay, that would be a no solution. And that would be really where you have two parallel lines. The other situation is where you have two identical lines. It's really two copies of the same thing. Okay, and those would be infinite solutions. Okay, oops. It's infinite solutions because every point on the line is an intersection. Okay, the two lines coincide. And so these are the three possible situations. You can have one solution, no solution, or infinite solutions. And they all are given different names. So I'm going to go through and define what each of these means, or what different terms are for each of these. First of all, we have something called a consistent system. Consistent systems essentially are those that have solutions. So they have solutions. Okay, so that would be this first case with one solution or the last case with infinite solutions. Then you have the inconsistent systems. And those are the ones that have no solution. That would be the parallel line case. Okay. Now, inside of the consistent systems, we actually have two subcategories. They're called the independent equations. Oops. And independent equations are basically two different equations. Okay, that would be this first case. So this first case here with one solution is a consistent system with independent equations. And then finally you have dependent equations. And the dependent equations are going to be the same equation. Okay? Or same lines. Alright, so we have our three categories. The first category up there at the top where there's one solution, that's considered consistent with independent. And independent equations. The no solution case here with parallel lines, that is inconsistent with parallel lines. And then the infinite solutions, we would call that consistent with dependent equations. Alright, so trying to cram a lot of information in there, so I apologize for my handwriting, but hopefully you got the gist of all of that. Okay?